All right, so let's see what the details of this chapter actually says. So we start out with a group G. G is precisely what was previously called X, right? So we just changed name because now it's a group. Apparently all groups have an identity element. I think I said that some groups may not have it in the previous lecture, but apparently they all have. Okay, so and then these groups, they are locally compact Hausdorff groups. It just means that as a set, this has a topology. Okay, that topology happens to be locally compact Hausdorff. Right, and then we need to multiply elements, right? So there is some map phi. I use phi too much, but anyway. So given x and y in this group G, there is a mapping that gives you a new element of G. And this is the group operation. So instead of writing phi xy, we're just going to write x times y, right? And then, as I said, all groups, at least in this book, have an identity element, which is such that the identity times x is equal to x times the identity is equal to the identity. So the identity for the real line is 0, but then the group operation is plus. Or we can have also the non-zero, the set with the punctured real line, and then with the normal multiplication, and then the group identity is 1, right? Anyway, when we have an identity, we can also define inverse, right? So how do we define, on the real line, what do we actually mean by minus x? Well, we mean the number such as x plus, which is the operation we have, and then this number minus x is equal to 0, which is the group identity, yeah? So in general, if you have just a group, you have some element x in the group, then x minus 1, now we use multiplicative notation, so then the minus doesn't go in front, but it goes here. X minus 1 is defined such that when you multiply, well, okay, yeah, all right. So now here's a problem because we don't assume it's commutative, so you can define it like this. So there is a unique element such that does this. Okay, you have to do some group theory to prove that. But then you can also flip the order here, right? And then that's a theorem that these are actually the same. Yeah, so it's a simple computation to check that inverses are unique and that if you have an inverse from the left, also an inverse from the right. Just go to Wikipedia and look it up. But anyway, so here now we have a group operation and we have a topology. Usually, when you do basic algebra courses, you just study the group structure without the topology. So the first chapter here, 9.1, is basically just about results connecting the topology with the group structure. So what you want is that phi as a function on G times G into G, you require that to be a continuous function. If this is set up right, you have a meaningful topology, then you want this group operation to be a continuous operation. So technically, this just means that take an open set here, send it back, and then you get an open set in the product domain. But then, of course, this is something that takes a while to understand. So basically, 9.1 is just a bunch of results, which if you translate to real line or whatever, are completely natural. So let me just make a one pit stop. So anyways, I'll zoom in on one result that maybe is a bit interesting. So to talk about uniform continuity. So how would we define uniform continuity on group? So if we have the real line, the definition for all epsilon bigger than 0, there exists a delta bigger than 0, such that a function f is uniformly continuous if f of x minus f of y is less than epsilon for all x and y, such that x minus y is less than delta. All right. So how can we translate a statement like this now to the group setting? First of all, note that this one, we can write it like x minus y is inside the ball with center 0 and radius delta. 0 is now the group identity element, right? A ball, speaking of a ball, it requires you to have a metric. So we don't necessarily have that, but what we have is something called an open collection of neighborhoods of a point that defines the topology. So this is going to topology course, but it's a natural concept, right? So if you take a point and then you just have a collection of smaller and smaller, like balls or whatever you want to call them, and then you say that this point belongs to an open set, some set here. If you can find one of this collection of smaller and smaller balls inside that open set, and then you just define open sets to be all sets which are open with respect to this definition, at every point. So this point will have a different collection of open neighborhoods. So you replace balls with some radius with a collection of open neighborhoods of every point. Now, since we have a group structure, we have a continuity of this guy and so on, it actually turns out that if we let this be the identity element E, and we have an open neighborhood, a collection of open neighborhoods of E, then we can transport that to any other point by the continuity of multiplication, right? So if you have like maybe they're countable, not necessarily, but let's say they are U1, U2, U3, and so on. If these are the open neighborhoods here, so smaller and smaller and smaller of the identity, and then this is your point X, then X U1, X U2, and so on, is just your collection of open neighborhoods of this guy. All right, so that's how we build the topology here. Right, so now getting back to this statement here. So here I have a small open neighborhood around the identity, so that X minus Y is inside of this. So uniform continuity, then in the it's smaller and smaller. So this was the example, the uniform continuity of G. Man, this is beautiful how I complicate things that for no good reason. Now, right, so what should we take? So a function, now we consider a function f on the group with, let's say, real values. And then we say for every epsilon, there exists an open neighborhood U of the identity element E such that f of x minus f of y is less than epsilon. So far, so good. But now when x and y are close, this is what this says, right? If x and y are close enough, then this is smaller, and this is like independent of where you are in space. That's why it's important to work here with one specific neighborhood around 0, so we need a translation. Otherwise, I could just say, for all y in a ball around x, but then this ball can, depends on x also. We don't want that. That's the whole idea with the uniform thing, that this does not depend. It's not like for every epsilon you take a delta. That's just continuity. If you start with x, for every epsilon there exists a delta such that yada yada. That's continuity. Uniform continuity is you start with epsilon, then comes delta, and then that holds for all x and y, right? So the same idea here. So then what we're going to write here is if x, y minus 1 is in U. So for every epsilon bigger than 0, there exists an open neighborhood U of the identity. So yada yada. Here we have now a problem because we could also have chosen this. And that is not the same necessarily, because the group is not necessarily commutative. And yes, the inverse, the left inverse and the right inverse is the same, but that doesn't mean that if you multiply with a different element, x in this case, it's the same whether you put it to the left or to the right. So this leads to the concept of, if you pick this one, then you get right uniform continuity, and if you pick this guy, you get left uniform continuity. And then you can go on to proving statements like, for example, if you take the compact functions, the continuous functions with compact support on G, which is all functions if G is a compact set and otherwise subset of that. So the statement is that all such functions are uniformly continuous. So the nice thing here is that actually, if you know the proof for how you do this on just an interval from analysis 1, then the proof here, it doesn't add anything new really. So getting through this results, there's not a one long, like deep result here. So they're all pretty natural. So it works with these things like this, like, okay, if you have a compact set, if you have an infinite covering of open sets, then you can choose a finite subcover. Stuff like that you need to know. So then if you have your compact set K here, and then you have your a sequence of open neighborhoods of a point that defines your topology, and then you start moving it around by multiplying like x like this, and every point has its open collection of neighborhoods. And that if you take the union of all x in K and all open neighborhoods, then that's an uncountable collection of open sets covering your compact set K. But then it's compact, so you can choose a finite subcovering. Stuff like that, you juggle, and you get results like this one. That's 9.1 for you. Now, moving on to 9.2. All right, so now let's get ready for the proof of the Haar, the existence of Haar measure. This is mathematical death metal. I mean, this, get ready to get your mind blown. If you're a math nerd, you're really gonna like this. If you're not into math, you're gonna start wondering if, why you didn't study modern art or some other shit, which is also abstract, but not that hard to understand. And I need to find a pen. So this theorem relies on some heavy-ass topology, which is actually super nice. If you took the course in topology, and there's this Tikhonov compactness theory, uncountable products of topological spaces and yada yada. And when you read that the first time, it's like, what the fuck is this possibly useful for? And then here we're up to constructing something very concrete, right? Like if you think of this, the group of unitary matrices, you want some sort of invariant, rotation invariant measure on that. It's a very concrete thing, and it goes through that Tikhonov theorem. And so, right, if you don't have a course in topology, then just lay back and maybe try to soak in some ideas and get a feeling for why topology is actually useful, but it's going to be hard to follow the argument. So we have this round object D, somewhere here sits an identity E. We have a neighborhood, a collection of neighborhood around this point E, which we're going to call it U with a curly U. So this is, it doesn't need to be countable. It's easier to think about it. So collection of open sets around E that defines our topology. Okay, so this is what we have to work with. And now take some guy here, K. What's the size of him? How could you possibly approach that question, right? But it's very nice, the ideas they have here. So, okay, so what's the Haar measure that we know? It's the Beck measure on the real line. And it's unique only if we decide to take the interval from 0 to 1 and decide that this guy, let's make it closed. So then it's a compact set. We want that length 1. If we change that requirement, then we get a different invariant measure, and they just differ by multiplication by constant, but we'll get to that later. So the point is, we're going to pick some set, we're going to call it K0, and we define this as our reference set, right? Just like, so this is our K0 here, yeah? So we're going to construct the measure so that he has measure 1, right? And then so everything is going to be measured in terms of how big is he. And it's important that this guy then has an interior. So you need the existence of compact sets with some interior. So there are open sets inside the compact set. And I guess the existence of such follows by whatever in 9.1, or you have to assume, I don't know. But anyway, we have such a set. That's not right. I'm not trying to explain the details here. So we have such a set. Okay. Now, how are we going to measure the size of him? So here's a very nice idea. Of course, if I multiply now this guy, K0, right. So one way would be to say, multiply him with some x, right? And then that maybe lands here. Now it covers a bit of k. And then I multiply with a different x, and it covers, and like this, maybe I need 4 of them to cover him. And then you can start counting, like, okay, what's the minimal? So all these sets, this is like x1 times k0, this is x2 times k0, and so on. And then you can start thinking, okay, what's the minimal amount of such sets I need in order to cover him, and then say that maybe that's the measure then of this. If I need 4 sets here and I cannot cover it by 3, then the measure of him is 4, and the measure of this guy is 1. But this is too rough, right? Because this is a fixed guy. You can't, then the measure would just take integer values. So we can't do that. So what we're going to do is something which builds on this idea, but involves these guys. Yeah. So first of all, let me zoom in here. So, just take an open set U to begin with, and here's our K0. And the open set U does not need to be one of these neighborhoods of identity so far. And then you consider, x1 times u for some x1, let's say it's here, and then x2 times u here, and then you do this, yeah, until you cover your whole K0. Now you get a number, but of course that number depends on how you choose your x1, x2, x3, and so on, right? Okay, so first of all, this is an uncountable. If you do this for all x's, you get an uncountable covering of K0. So compactness tells you can choose a finite subcovering. But, okay, so each way of choosing points like this gives you a number, 15, then maybe you can get 14. But the minimum of all such possible numbers, that's a well-defined number, right? These are integers, there is some covering that attains that number. So we can actually define properly a number. Let me see what notation they use in the book. So K0 colon U is equal to the minimum of what we have here. Amount of balls, sorry, the amount of translations of U that you need to cover this. Okay, so this kind of tells us how big is K0 in terms of U. Okay, so now we have it here. Many small ones. But then we can do this, play the same game with this guy, right? So we get another number. Which is this. Now, if he's twice as big, it's kind of intuitive if this U is a small set, so that we don't have, there will be some overlap here, right? So this counting balls or counting amount of U's is not an exact measure of size somehow, but if U is smaller and smaller and you have very little loss here in the overlaps, then maybe the amount of balls should somehow correspond to the size. Okay, so if I want to know how much bigger is K compared to K0, well, I can consider then the quotient of these two numbers, and that I'm going to call it HU. Okay, so what I'm aiming for here is based on a reference set K0. I want to first give a formula for the measure of any compact set. Okay, maybe I should have said that already. So we were just working towards getting a measure for all compact sets, and then from there on, we lift it to open ones, and then we do this standard construction in the end with regularity of measures. So once you have a measure for the open, you know how to measure open sets, like how we're going to get back to the outer measures and all that, just like how we constructed Lebesgue measure in chapter 1, So the difficult part is getting a decent size for the compact set. The rest is like long, but more like transportation by now at least. So these ideas have already been settled. So now I get a fraction here, so I can, I get more fine values. But of course, this all depends still on U. So if this number here is 50, the size of K, you can't get finer by steps of 1 divided by 50 in size. And size is not something discrete; it's continuous. Well, it can be discrete, but it shouldn't be in general, right? So this has a dependence on U, which is unfortunate, right? So then, now is where we involve these guys. So we're going to have this collection of neighborhoods so the idea here basically would be to do limit U in U goes to 0, whatever that means, and then HU of K equals to the measure of K. This is how the whole thing is set up. Of course, what the hell do we mean by taking such a limit, U going to 0? It's not clear at all how to define it or what this even means, right? But maybe you can get a feeling at least for if I could take the limit somehow like that, then this would all make sense. And that's, in order to take that limit, that we need this Tikhonov business. Okay, so before we get into that part of the argument, we need to establish a few results here about this object here. And one of the results, I think there's a lemma which states a lot of results, and all of them are useful. But the one that I want to highlight here is the one saying this. This one is important. So it's kind of natural, right? So if I use my K0, as I first said, with the red ones, to cover my K, and then the K0 in turn is covered by the small balls in terms of U, then combining those, I multiply, right, I put all the balls, right, so here's the first copy of K0, and it comes along with a lot of balls. And then comes the second copy of K0 and it comes along with a lot of balls. So now I've had 4 copies of K0 and 15,000 balls here. I get, 15,000, 30,000, 45, 60,000 balls, and that's a covering of my K. Now, with translations of this guy U. So this number up here is clearly less than this one times this one. And that's what this thing says. So it's a natural observation. This is good because it puts an upper limit to the value here, what we can have. Because, all right, so this is now a function that for every compact set K gives a value. No, I got this mixed up. So what is the function on? Well, C, curly C, that be all compact subsets of my G. So the function HU is a function on C. But instead of thinking of it as a function that ends up in R, we're going to think of it more like a sequence. Right, so HU is a function on C with values in R. But then, if you think of the C as numbers 1, 2, 3, 4, 5, you can always think of a function on the numbers 1, 2, 3, 4, 5 as a function on those numbers, or as a sequence, which is, then you do by parentheses A1, A2, A3. So we're going to do kind of the same twist here. So instead of thinking of it as a function like this, we're going to think of it as a sequence. So we're going to think of HU as a member of the infinite product of compact sets. So for each compact set, I need to put here now a set. And what set do I put? I put, right. So if I want to think of this as a sequence, I could do the infinite product of just the realign with its set. Yeah? So what's the value then of this sequence? So pick a compact set K, and then the value in this uncountable product is just HU of K. So it's, just like instead of, like I said, with sequences, if you think of a function f of 1, and then you have f of 2, and so on, and you collect all those numbers in like a infinite row, and now all of a sudden you call it a sequence. So you can call this f1 instead. So this is just like playing with nonsense. But the thing is, at the end of the day, it doesn't turn out to be nonsense. So, all right, so I have this infinite product here. And what we want is somehow the existence of some sort of limit here. And usually then you need some sort of compactness. And this is bad choice now because R by itself is not a compact thing. So if you do an infinite uncountable product space of something which is not compact, you're not going to get something which is compact. So we're going to switch this with the interval, because we know this with the interval from 0 to this upper bound there. And this is a closed bounded interval, and we know that the value HUK is in this interval because it's a positive number, well, non-negative number, and right. Now this guy is compact. And here's this Tikhonov very bizarre theory. It's used also in functional analysis to prove something called Alauger's theory. The unit ball in the weak topology is compact. It's also weird as argument like this one. But anyways, so now this is a new topological space X. We're gonna define it X, and then this space needs a topology. So then there are different ways of defining topologies on this one. So as I said, if you haven't taken topology course, just forget about this. But basically, if you think about all compact sets, which is somehow our enumeration set here, as just a line, and then a basis of open sets, like, okay, zoom in on this guy, K2 and K3. And then you say, okay, here I have an open set. So on this axis, we have the real line now, like I did first before I restricted it. So, or whatever is on this axis. Like we see here, you don't need to have one axis here. You can have one set for this guy, another set for this guy, and another set for this point. But if we have the same, so you can paint it. And then I take an open set here and an open set here. Then you define something to be open here. So you can do U1, U2, and U3. Then you just, this defines like a basis of open sets. Well, this defines an open set now in the product space where you just, so you do a U, is now a subset of your infinite product, whatever it is. Let's say I'm back in the R situation. So then U is equal to all sequences H such that H of Kj is in Uj, right? So in a sense, this is saying, if I have a function here, H, it's in my set if it passes through here and here and here, but I don't care jack shit what it's doing outside as long as it passes through these three sets. Now this gives me a topology with many open sets. I mean, the other alternative thing would be to say that for every K, you should be in this set and in that set and in that set, then you get some sort of strong topology. That one has very few open sets, and therefore it's much harder to work with. So the weak topology here is good because of this Tikhonov theory, which says that if we work with the weak topology, then if all of these guys we use to define our product space is compact with the weak topology, then the product space is also compact. Fantastic result. Okay, what do we know of compact sets? So the first one is, okay, you have your set K, take your open balls, and you have infinitely many open balls, and then you can always choose a finite subcovering, right? So if K is a subset of infinite union alpha in A, U alpha, where these guys are open, and alpha A is just any indexing sets, then there exists alpha 1 to alpha n such that K is a subset of the union J goes from 1 to big N U alpha J. This is the most commonly used one, but you can flip this around and flip around it. In the book, they just say De Morgan's law says something is equivalent. I don't know, you have to think about it a bit. But this is a theory in topology that there is an equivalent characterization in terms of closed sets. And how does that one look like? So now, again, you have your K. And you don't necessarily need a covering any longer, but you have, let me paint closed sets like boxes like this, right? So let's say you have a bunch of closed sets, let's call them C alpha. So C alpha, alpha in A. This is some sort of, it's just a collection of closed sets in here. But then they can have some property which is called the finite intersection property, which says that anytime I look at the intersection, let me write like this is a bit. So if I take a bunch of point alpha 1, alpha 2, up to alpha n, and n is free, and I look at this, then I want this to be not equal to the empty set. If that happens independently of how I choose these points and independently of what m, then I have the finite intersection property. And then the characterization of compactness is that if you have the finite intersection property, you also have the infinite intersection property. So if this is true for all sequences alpha j from 1 to n, n is free, then it follows that the infinite intersection alpha a C alpha is not equal to the empty set. Right. So how do we sew this bag together? Right. Now this is just fantastic. So then you go like, I have this all great ideas. So now h of u is no longer a function, it's a sequence in this weird space here. And then I have closed sets over there. Well, this is just an element, and those are closed sets. So how I'm gonna do this thing here, and then we're connecting some of this collection of open neighborhoods and have the open neighborhoods go to 0. Well, so what we're gonna do is, okay, we're not gonna work with a single function, we're gonna work with sets. So SV will be equal to the closure in this new topology of all the sequences HU, where U is a subset of V, and both U and V in this case here are this collection of open neighborhoods. Right, so now for each open neighborhood of the identity V, I get now a closed set. Now, here, if I start to do the intersection SV1 intersected SV2, then it's easy to see that there exists a guy in here, which is basically HV1 intersected V2. So these closed sets have the finite intersection property. Alas, right here. So now the intersection of V in the collection of open neighborhoods is not equal to the empty set. So there exists a guy, there might exist more. In reality, there has to be only one, but it doesn't matter now. There exists one, and that's the function h we've been looking for. Let's call that h with a big dot. And why he chose that notation, I have no idea. I guess he was tired of writing this book. This makes no sense. But anyways, this is in a sense the limit process I was talking about, because now this guy h dot gives me a sequence for every compact set here. I get a value. That value is, in this range here. And that value is somehow, this, no matter how small V is, there exists an HU, so that with U smaller than V, so that coincides with this guy, right? So in that sense, it is a limit process, because this is true for all v's, no matter how small v is, this h black dot is inside of that. So here now we have defined a sequence. This is still a guy, right? You know, this is a subset of X. So all sequences, if you want, like this. But now we switch back to looking at it as a function. So just for every, I'm out of Blackboard and shell instead of Arnold for a change. Gonna come and interrupt me at any point. So anyways, for all compact sets K, I can now define, I'm gonna jump ahead a bit. Mu of K is gonna be my H black dot K. Yeah, so I think of it as a function again, and this H dot is actually just my measure. Yeah, mind-blowing argument. Of course, we're not done here. Now it's like, but this is like the, I mean, here you really needed new ideas to get to this point. Now we have something we can work with. Of course, it's going to be complicated. It's a Mickey Mouse stupid construction. So you need to like verify so many things to pull out this argument to the end, right? But at least we have the idea of the construction. So by the time we have established basic properties of this one for, you know, whatever we want, like, you know, the measure needs to be additive. So if K1 and K2 are disjoint, we want H blob of K1 union K2 to be the same as H1 K1. So H blob K1 and H blob plus H blob K2 and yada yada. But so we need to verify a lot of things. But we have some idea of how to define this guy. So what we're gonna do now is now you just take an open set, any open set, like I'm calling it U again, but, and here's the group G. Now what's the measure of that? So then we define an outer measure, U star of U, equal to the supremum, H blob K subset of U. All right, and then you have to think, okay, what properties do I need of him in order for this to behave like an outer measure? And then you prove that. And once you have this, then you do mu of any set A to be equal to the infimum, mu star, there should be a star there as well, U, and then you do like this, right? Actually, here I'm just guessing. I need to double check that that's what they actually do. But this is the natural way to go on about it now. We have been through this argument at least 2 times in chapter 1, and in the Reed's representation theory, we did something similar. So most likely that's what's going to happen. Yeah, look at that. I was right. And even at this point, there's another page of computations. So once we're here, we have an outer measure where we have to verify that it's an outer measure. And then at the end of the day, we need to verify that if, I'm tired of you, if V is open, then it is measurable. So mu star V is equal to mu star V intersection V plus mu star V intersection V complement. And once we have that, we know that the open sets are measurable, meaning that the outer measure mu star gives rise to a measure U on some sigma algebra and mu star, but if the open sets are measurable, then the Borel sigma algebra is a subset of that. So we have now measure mu, which is Borel measurable. And of course, all right, why is the translation invariant? Well, at least that's easy to believe, right? Because the whole thing set it up by just fixing a reference point and then moving it around by translations. Yeah. So if this guy K moves up here, then I just do my translations over there. And right, so if I have this K here and I move him by a translation, and then the covering, I just move it by a translation as well. So the way of counting balls that we set up in the beginning doesn't see translations, and then the HU function is not going to see translation, and of course at the end, this limit guy is not going to see translations. Beautiful, beautiful mathematics. And now I'm actually out of time. Shell still hasn't appeared, but right. So at the end of 9.2, they should prove that this guy is unique. So as long as you decide what's the measure of K0, then there's only one guy left Haar measure. Then of course there's right Haar measure, and then you just repeat the whole process again. You could do that, or the way they do it here is they fiddle with some. They use the left Haar measure to define a right Haar measure. So there's a shortcut to it. And well, that's the end of 9.2. And now Shell is here. So what's written in 9.3, you will never know. All right, I'm back. I want to explain this stuff in the end as well, due to my benevolence. Okay, so remember the first lecture on Haar measures where I spoke about this like unitary group of unitary matrices is a compact, not only locally compact, it's a compact Hausdorff group. And all right, so now there's like a right Haar measure and a left Haar measure on this. And it's like, but intuitively, there should be just one kind of Haar measure, whether you multiply with matrices from the right or from the left, right? So I'll like in that lecture, I use gamma now for Haar measure. So left Haar measure satisfies right? And right Haar measure. So this does not necessarily mean that you have this for all y. This how happens for all x. So if you have a measure, and I'm going to put the inverse hat on it just because they do it in the book, under the notation. But if you have a measure that does this, then you call it right Haar measure. And what we want to establish here, what I'm aiming for, is to show that if your group is compact, then there's only one. So both of them are the same. So this is possibly not equal to that, but doesn't need to be not equal to that. So if we now have the left Haar measure, how can we construct from it a right Haar measure? It's pretty easy. You define it like this. So you work with the inverse, yeah? Because the inverse flips orders, right? So now, if you put your x or y here, then when you do the inverse, it's going to end up in front. And then if it's the left Haar measure, it doesn't see it. And then by the definition again, you have that. So now this guy became a right Haar measure. So to start understanding somehow how to relate, all right, so this you can use then to, given any left Haar measure, you can construct right Haar measure this way, so you don't need to do the construction from scratch. So you just use this, and they also prove in the beginning uniqueness. So as long as you take some set and decide that this set is going to have size 1, then the left Haar measure is unique, and the right Haar measure is also unique. And then there's nothing fishy with that. But here's a sequence of very elegant, simple ideas. There's nothing deep here, but still not maybe so easy to see. So if I now have the left Haar measure, and I'm curious to find out what does this operation do? Now, of course, since this is a left Haar measure, I have this identity for all y, right? X being fixed. Meaning that somehow the new measure that we can call it like, I don't know, gamma x. Probably is the notation in the book. I didn't like really the notation. Anyway, this is my notation now. So gamma x with the fixed x is now another left Haar measure, which means since left Haar measures are unique except for multiplication with some constant, that there must be some constant which we can call delta of x, such that gamma x, also, yeah, right, so such that gamma of ax is equal to delta x times gamma of a. So all like right translations of our set A, we can get by just a multiplicative constant in front. And then now you can imagine that you can prove various stuff about this one. So for example, there's a theorem in the book, you look at the details, this guy is continuous and multiplicative. Continuity is pretty natural, right? We kind of set up things. Well, anyways, it's a short proof. And multiplicativity is just this. Is completely immediate, right? Because if I stick in an x times y here, okay, let me do the computation. So delta x times y, okay, let's not do it. X times y is delta of y, and gamma ax, which in turn is then delta y and delta x, gamma of a. And then, of course, well, here more immediately say this is delta x y and gamma of a. But this has a very funny consequence. So continuity, armed with this multiplicative property, shows that if the group is compact, then this function is actually unimodular constant equal to 1, which basically means that, you know, where's the identity? It basically means that, well, it means that these two are the same thing, right? It means that, where is this stupid? Here. If this guy is 1, then my left Haar measure is actually a right Haar measure, right? So how can we see this? Well, suppose that this number is not equal to 1. Raise it to the power n, use this rule n number of times to get this insight. Now you know that a continuous function on a compact set is it's always bounded. So if this number is not equal, if this number is bigger than 1, this is unbounded, that's a contradiction. This number is smaller than 1, well, then you just fiddle with the inverse instead. So if it's smaller than 1, you put a minus n here, you get a minus n up there, and then this goes to infinity with n. So again, contradicting that this has to be bounded. So therefore, poof, like a rabbit out of a hat, the damn thing has to be 1. So left and right Haar measure, no difference as long as the group is compact. I guess I haven't even said, for me, bad of me, teacher, what is actually the Haar measure for the multiplicative group on the real line? So we know that Haar measure for plus and minus is like Lebesgue measure, right? Which Haar measure, which measure satisfies, so let's do, we want to measure in the positive real line such that x
times some set A is equal to that set itself. Well, maybe not so obvious, but the answer is as follows. You integrate, so gamma of A is equal to the integral over A 1 over x the lambda. Or maybe I should say 1 over t or something. And I fixed x here. Why? It's actually a computation. So if I do gamma times xa, doesn't matter here which side I put it. I mean, this group is commutative, so then obviously our measures are the same from the left and the right. So this shows that our measure actually, also Lebesgue measure. If you have a locally compact group which is not compact, it can still be the same, but not always. I don't know of an example where they're different, but I guess the exercises should have some example. Anyways, so we integrate here over the set x times a 1 over t d lambda. So now I do a change of variable. So this is, we know that, all right, I can just use Riemann integral. All right, so this is a very complicated set, and even not, but let's say it's, we can prove this for intervals and just lift it to something bigger than intervals by this regularity process or whatever. So then I put an interval here, and then I use my Riemann integrals, so I can do variable. And then my new variable will be x times s, s being the new variable. So then the inner derivative, t equals to x times s is x. So the TDS is equal to x. And then the s. And now, if I want t to be in x times I, then s needs to be in I, right? Now this x here and that x there disappears. I get gamma of I. Nice. Right, and then he has a proposition here in the end, which seems to be a bit hard work to get to. That, all right, if this guy is not unimodular, then, I mean, this relationship we have here, where did we define here? This is the definition of the unimodular guy, right? It doesn't really tell us, I mean, it tells us how to compute the right translation, but if we want to integrate against the right Haar measure being armed with the left Haar measure, this doesn't really tell us how to do that. But that's what he's proving here. So what you can do, if you want the right Haar measure of a set gamma of A, you can integrate this modular function against the left Haar measure. So that's a nice observation. And I got it wrong. You have to put a -1 up there. Let me wrap up this lecture by connecting to where I started this like matrix theory or random matrix theory. You want to put probability measures on spaces of self-adjoint matrices. Right, so U of n is a compact Hausdorff group. So there exists a unique Haar measure. Well, unique left, right, both left and right. Okay. And then remember, we were studying the thing. It's natural to study measures. Okay, so if I take some sort of set S, subset of the Hermitian matrices n by n, and I do left and right multiplication with a unitary matrix, then it doesn't see it. Yeah. Now, for unitary matrices, we have that this guy and these two are the same. Yeah. And we just established that for Haar measures where the left and the right are the same, we have that if I have a set, okay, now I don't know, what should I call a set in here? I call this guy S, maybe I call him T. Stupid, ugly looking notation, but anyways, this was a way to define the right Haar measures. If we know that they are the same, you see that there's no difference here of doing the Haar measure on this guy or that guy. So this doesn't maybe really prove anything, but still, yeah, it kind of leads to the fact that if you have like the pullback maps, you start with any matrix A and you pull it back to this guy and that guy, then you somehow you don't need a right and a left Haar measure to deal with this situation. I mean, clearly here, if I stick in a V here, then I get a V star there. So I have some sort of right invariance, and I put a V here, and I get a V star over here. So I have some left invariance as well. But since the Haar measure is both left and right invariant, we can believe that doing the pullback here, we have that mu of some set S is equal to the outer product of mu and gamma, where mu acts on the pre-image of diagonal matrices and gamma acts on the image of those guys. So I don't know how I should formally write that. If this map is called phi, actually that doesn't make sense. I need to call it better to go the other way. So this is my phi, because there are different representations that give the same guy here. So you can like multiply a column here with some unimodular number, for example, and then it all cancels out because we have this like relation here. So there are different compositions that give the same guy, but they are all trivial variations of each other. But then this is not an injective map. But then we can establish some formula like this, where this now again is a measure, okay, acting on diagonal n by n matrices. So in the end, mu is just a measure on Rn into R. So this is something we understand well. Okay. Right. So then now there's still one chapter left. So 9.4, and we're kind of there now. So let's say we're studying, we do random matrix theory, right? So we have some measure like this, and we want to somehow, we randomly generate matrices, and this measure mu tells us what's the probability that a certain set of the matrix is in a set of a given set, you know? So then we have this measure mu on, in this case, that guy, and then it's natural, okay. So then you start thinking of other ways to, well, it's very natural to, I can't go into, to do function theory now on this kind of space, right? So anytime I have a locally compact group or a compact group, then, okay, I want to look now at functions. So I was going to say that in this situation, this could be some probability density function, but then you actually need two to begin with. Yeah, so if you don't have a uniform probability, but you have your Haar measure, then you can look at some probability density function here. Well, so you want to know what are the integrable functions on this group, and then you want to know the dual, and it turns out that the theory is copy paste from what we did in chapter, well, starting in chapter 2 and ending in chapter 4. It works out just as well here, basically. So the dual is L infinity. The next time I will start talking about probability theory, and there it turns out that convolutions are very important. And so this L1 of G is not only a interesting function space, but it's also an algebra in itself. Then you need some sort of operation. If you think of L1 of R, and you take two functions f and g, then how can you create a new function in L1 of R, somehow like the multiplicative structure? Well, you can do the convolution. Right? And as a small exercise with Frobenius theory, you can see that if these are positive functions, then the norm of this guy is actually equal to the norm of f times norm of G, L1. So it's nice, you multiply we do the convolution, you think of it as a multiplication of two L1 functions, so you get a new L1 function. Moreover, this happens in a sort of modular way, so the norm of the new one is just multiplying the norm of the two previous ones. So that's on the real line. So if you're on a locally compact group, what would be the counterparts? You have a function now, scrap this, your functions are living here. And then instead of this, we do drums, poof. Yeah. Or something very close to it. He puts it in a different order. I don't think it matters, but maybe it does. Oh, and then it starts to do convolution of measures as well. Oh, it's getting a bit far out, in my opinion. And that's the end of chapter 9. Thank you.